welcome to our channel Pharmatude, and our topic is solubility of liquids in liquids part 2. So in our previous video we have discussed regarding some of the basic terms which are essential in order to understand the phenomena of solubility of liquids in liquid and also regarding the CST, that is the critical solution temperature, and what is the role of critical solution temperature for partially miscible solution. So now in this video we will be discussing regarding the following topics. So first one is the Raoult's law, then the negative deviation from the Raoult's law, then the positive deviation from the Raoult's law, and lastly the azeotropic mixture. But before studying the Raoult's law, we need to understand the difference between the ideal and the real solution. So what is ideal solution? The ideal solution is one in which there is no attraction between solute and solvent molecules. And in a real solution, what is that? In real solution, the cohesive force of attraction between A exceeds the adhesive force of attraction which is existing between A and B. So now what is cohesive force? The force of attraction present between the unlike molecules is called cohesive force. And what is adhesive force? The force of attraction present between the like molecules is called adhesive force. So in ideal solution, what happens that there is no attraction between the solute and solvent molecules and they simply form a solution. While in the real solution, what happens that they form a different types of solutions like the homogeneous solution or the heterogeneous solution, and then depending upon the force of attraction they form a solution. So in ideal solution, there is no change in the property of the components other than dilution. See, whenever there is an ideal solution, all the properties of the components present in them, they have a similar property, or simply we can say that while forming an ideal solution there is no change in the property. Except there is a change in property which includes like dilution. Sometimes due to the dilution the ideal solutions properties got changed. And what happens in real solution, that the attractive forces between A and B may be greater than those of between A and A or B and B. So here what happens that the force of attraction between the solution or the solution molecules may be greater than that of the individual force of attraction of the solute or the solvent molecules, while the ideal solution obeys the Raoult's law, while the real solution do not obey the Raoult's law. So now what is Raoult's law, which will be knowing in the upcoming slide, and we can see practically that there are no ideal solution, but in our daily life or in our lab scale we are having mainly the real solutions. Now what is Raoult's law? In ideal solution, the partial pressure of each volatile constituent is equal to vapor pressure of a pure constituent multiplied by its mole fraction in the solution. So what happens here, that partial pressure of A, or this is the statement given by the scientist Raoult, and then based upon his statement we came into a mathematical equation that the partial pressure of A, or simply the partial pressure of component A, can be obtained by P0A into XA, and here P0E is the absolute or pure pressure of A into mole fraction of A, while Pb is equal to P0B into XB. So what is Pb? So Pb is, or the P0B is the absolute partial pressure or absolute pure partial pressure of Pb, and XB is the mole fraction of B. So we can understand this Raoult's law from this graph, and for the students it is very essential that whenever in the examination you are asked the with a short note on the Raoult's law, then you have to draw this graph. So this is the vapor pressure composition graph for an ideal solution or simply a binary mixture. So here we can see that there is a binary mixture of benzene and the ethylene chloride. So here the solute is the ethylene chloride and benzene is the solvent. And here the graph plotted is between the vapor pressure and the mole fraction. So here we can see that the mole fraction of benzene is 1 initially, but as we move from left to right towards ethylene chloride, the mole fraction of benzene tends to 0, while in case of ethylene chloride there is a completely vice versa phenomena, that a mole fraction of ethylene chloride is 1, but as we move from right to left, the mole fraction of the ethylene chloride decreases. So what happens here, that if we plot the graph for the benzene regarding pressure, and then we can obtain the partial pressure or the pure absolute pressure for benzene is 236 mmHg, and the partial pressure of benzene can be obtained by P0A into XA. While if we plot the graph for the ethylene chloride, then the partial pressure or pure absolute pressure of the ethylene chloride is found to be 268 mmHg. So the partial pressure of the ethylene chloride can be obtained by P0B into XB. So by combining the partial pressure of benzene and the ethylene chloride, which is obtained by the calculation, or we can say simply from the Raoult's law, we can get the total vapor pressure. Now sometimes what happens, that the deviation from Raoult's law occur, and this deviation can be a positive deviation or a negative deviation. So what is negative deviation from Raoult's law? When the adhesive attraction between the molecules of different species which exceeds the cohesive attraction between like molecules, then the vapor pressure of the solution is less than that of the expected from the Raoult's law, and so due to this negative deviation occurs. So why negative deviation occurs? So in the first line you can get the idea that whenever the adhesive attraction, and so we can simply say that whenever the force of attraction between the like molecules of different species, which is quite more than that of the force of attraction between the unlike molecule or simply cohesive force, then at that time the negative deviation occurs. So what occurs in negative deviation? That the actual partial pressure or the summation of the PA plus PB is less than that of the total partial pressure or the actual value which should be obtained, and so at that time, as the partial pressure is less than that of the actual partial pressure, so we obtain the negative deviation from the Raoult's law. And here example is chloroform plus so here example is the chloroform plus acetone. So we can also understand this by this graph method, or simply by plotting the graph, that we can consider that there are two solutions, A and B, where A is solvent and B is solute. Initially what happens, that the mole fraction of A is 1, but as we move from left to right, mole fraction tends to 0. And similarly in case of B, there is a vice versa. Initially the mole fraction is 0, but as we move from left to right, its mole fraction increases to 1. So if we plot a graph for XA or simply a PA, then we can achieve a P0B. At that point we obtain the pure absolute pressure of B, and if we plot a graph for PB, then we can obtain the pure absolute pressure of A. So by simply combining the PA plus PB we can achieve the total partial pressure. So that total partial pressure which is obtained is its value is quite more than that of obtained by PA plus PB. So as a result, negative deviation occurs. Now the positive deviation. So when the positive deviation happens, when the interaction between A and B molecules is less than that of between molecules of pure constituent AA or AB, the presence of B molecules reduces the interaction of the AA molecules, correspondingly reduces the BB interaction. So whenever the interaction between the solution molecules such as A and B, consider that A is a solvent and B is a solute, then the force of attraction between A and B molecule is quite less than that of the individual constituent present in that solution. For example, force of attraction between AA or simply the force of attraction between BB, they are much more higher than that of the force of attraction between A and B. So as a result, positive deviation occur, and so due to this, the dissimilarity of the polarities or internal pressure of the constituent results in a greater tendency of both the molecules A and B molecules. So due to the difference in the polarity or due to the internal pressure change, what happens that the tendency of A and B molecules or a constituent results in a greater difference in the polarity of A and B. So the partial pressure or partial vapor pressure of the constituent is greater than that expected from the Raoult's law, and the system is said to be positive deviation. So what happens? PA plus PB, the value which we obtain is far more greater than that of the actual partial pressure which is obtained from the Raoult's law. So here example given is benzene plus alcohol or benzene plus ethyl alcohol. So here we can also understand this by the graphical method, that similarly we have seen in the negative deviation, it is means totally similar to that of negative deviation, but there are some of the changes in that which we have to note. And so initially XA is solute or simply a solvent and XB is a solute. So initially the mole fraction of XA is 1, but while it moves from left to right, the mole fraction reduces to 0, while in case of XB the mole fraction is 0, and as we move from left to right, the mole fraction is 1. So what happens here, that if we plot a graph for PB, then we can obtain the P0B or simply the pure absolute pressure of B, and if we plot the graph for PA, then we can obtain the P0A or simply the pure absolute pressure of A. So now by combining this PA plus PB, we can obtain the total pressure. But what happens, the summation of PA plus PB value is much more higher than that of the total pressure. So due to this, positive deviation from the Raoult's law occurs. So now it is the last topic of this video, that the azeotropic binary mixture. So what is azeotropic binary mixture? It is simply the mixture of two liquids that has constant boiling point because the vapor has the same composition as the liquid mixture. So in the azeotropic binary mixture, what happens, that whenever there are two solutions, so that two solutions have a constant boiling point, and this constant boiling point is there due to the same vapor present in that liquid mixture. The boiling point of an azeotropic mixture may be higher or lower than that of any of its components. So this boiling point can be higher or even can be lower than that of its components. So there can be variation in its value, and the component of the solution cannot be separated by simple distillation method. So here what happens, that the component of the solution, they can't be separated simply just by distillation. For them, the higher analytical techniques are required. So now in our upcoming videos will be on phenol water system, then nicotine water system,